So the next talk is going to be by Weiqi Zhang, a second-year PhD student in the Department of Chemical Engineering at the University of Wisconsin-Madison, advised by Victor Zavala. He's generally interested in optimization, market design, and computational software development. Okay.
Okay. Can everyone see my screen now?
Yes.
Okay. So I'll get started. Hello, everyone. My name is Weiqi. Today, I will be presenting our work on using the concept of virtual links to capture flexibility from data centers in market clearing framework. So first, I want to motivate our work by talking about flexibility in power systems. So flexibility is an important resource of power system, which refers to any ability to maintain balance between electricity supply and demand in real time. And this is a difficult job because of the uncertainty in real-time power system operation. For example, in recent years, we see an increase of renewable power adoption. This trend increases need for more flexibility because of the huge uncertainty in some type of renewable generation, such as wind and solar energy, as we can see from this figure here. An important result of inflexibility in power network is price volatility and negative prices. So here at the bottom is a price map of California ISO in 2015. We can see that the prices increased to extremely high, like the 300 level, and then come back to normal level in just 20 minutes. And also in the first snapshot, we can also see large price variation in space and even like negative prices in those blue regions here. So as the prices become unpredictable, infrastructure investment and operation also become more risky for potential and current participants. So traditionally, power systems obtain flexibility from sources like flexible power plants that can ramp up and down. So in this work, we consider data centers, which are recently becoming a promising source of flexibility. So data centers are large-scale computers that essentially provide computing services to businesses and personal customers. A major trend of data centers is that they are becoming very large loads. So we can see from the figure on the left that in 10 years, data center will consume 20% of the total electricity across the globe. However, on the other hand, data centers are also aggregating into what we call hyperscalers, meaning that large computing power is concentrated into a few very large servers. So this figure here shows that half of the data center power consumption comes from those hyperscale data centers. And if we look at the data center map for major IT companies in the United States, they consume a lot of power, but only with a limited number of data centers across the country. So these trends are implying that data centers can offer new types of flexibility to power system. So data centers can offer new flexibility by shifting computing loads in space via data communication. So for example, let's say if we have a computing job submitted at this place, like near Seattle, the operator can choose to transfer the code and data to another place and execute it at the location if they have a data center site here. Another thing that they can do is data centers can also store workloads temporarily to execute them later, which means that computing loads can also be shifted in time. So in this case, we are specifically talking about flexibility from workload shifting instead of shifting energy for cooling, which has been explored by many previous works about data center demand response. I also want to mention here that practically there are a few drawbacks for data centers to use this flexibility. So for example, temporal shifts or workload delay will lead to higher computing latency, which is not desired. And the spatial shifting would require multiple copies of data center to be available across the different sites, which can be expensive, especially when the amount of data is large. An observation I want to make here is that load shifting in space is similar to transmission lines in that they are both matching electricity demand and supply across different places. However, the current market designs that we know of so far do not capture this type of load shifting flexibility, and we need to identify markets that can properly incentivize that. So now I want to talk about how we incorporate flexibility into market clearing models. Before actually getting into flexibility, let me start with a quick review of electricity market clearing. So electricity market clearing is the process that an independent system operator, or ISO, decides electricity price and allocation that are economically optimal and physically feasible. To do that, the ISO collects bid information from participants like loads, generators, and transmission lines, and then outputs the price and allocation by solving an optimization problem. So the bid information usually consists of a price and a capacity. So the bid price tells the price level at which a participant becomes willing to participate, while the capacity tells the maximum amount by which it is able to participate. So with that, here is the optimization problem that the ISO solves. So the objective is to maximize the social welfare function, where we maximize the total value of load served and minimize the cost of generation and transmission. The problem is subject to power balance constraints on each node, and the dual variable of these power balance constraints are used as the clearing price, or LMP. The DC power flow constraints here provide a simple physical model of transmission for the market clearing. In the end, the allocation variables, DPF, are subject to the capacity bounds, which are defined by the bid capacities. So one thing I want to note here is that we have a cost term for transmission on the objective function, which is not a common practice in power system optimization. We add this term in order to highlight the relationship between the virtual links and transmission lines. And I will show more details on this later when I talk about virtual links. But in practice, the bid prices for transmission lines are mostly set at simply 0. So now I want to introduce the concept of virtual links. Virtual links represent the ability of non-physical load shifting that data centers are capable of. So as you see, like these yellow dashed lines here, each virtual link connects two nodes to capture how loads flow, how computing loads flow between data centers that are attached at these two nodes. So if you look at all the spatial virtual links here together, the network of these virtual links can be seen as an additional layer of infrastructure on top of the physical transmission network, which are the solid black lines here. So the network of virtual links serves the same function, again, of matching demand and supply across space. However, it is not subject to the power flow physical laws. So with the virtual links, the computing loads cleared at a location are not just the loads submitted at that node anymore, but adjusted by the virtual link quantities. So our new market clearing model now incorporates virtual links like other participants. The social welfare function here minimizes virtual link costs in addition to original. The power balance constraints capture the load flow through the virtual links. The DC power flow constraints are not changed because virtual links are not involved. However, we need to include a set of new constraints here that capture the computing capacity of each single data center. So basically, the loads that are physically cleared at a machine should be bounded by the machine capacity. In the end, we include the operational range for virtual link allocations. So how does our market pay for the virtual links? Each unit of virtual link is paid by the price difference between the nodes that virtual link connects. Again, similar to how markets usually pay for the transmission lines. So this is a key to how our market clearing model incentivizes flexibility from data centers. The payment for virtual links becomes additional revenue stream for data centers. And essentially what they do is they enable data centers to have access to cheaper electricity, have more access to cheaper electricity actually. So therefore, we could also expect price volatility of the market to decrease with virtual links, since now data centers have an additional way to take advantage of the price volatility. We can also extend the virtual link idea to capture temporal flexibility from data centers. So to do that, we use the nodes to represent each discrete time point, and the virtual links to represent the workload delay to a later time. So again, the temporal virtual links work similar to storage dynamics in that we are storing workloads for later clearance instead of storing electricity in energy storage applications. So following this reasoning, we can generalize our virtual link concept to represent flexibility from space-time load shifting. The market clearing uses each node to represent a space-time pair now, and each virtual link will connect a pair of space-time nodes here. So the changes to our market clearing framework is quite intuitive to capture space-time flexibility. Basically, we index our decision variables by the additional time dimension here, and the original constraints like the power balance and the DC power flow and everything else will be broadcast in time dimension too. So now let's look at some case studies that demonstrate the behavior of our model. I will present 3 case studies in total. The first 2 small-scale case studies will capture spatial and temporal flexibility separately, and the last one will be a larger IEEE 30 bus case where we consider space-time flexibility together. So the first case study is the 3-bus node network on the right here, where each node is connected to a generator and a data center, and each pair of nodes is connected by a virtual link and a transmission line. So we start with the 4 cases here at the bottom, where we fix the bit price, but gradually increase the virtual link capacity. So the virtual link capacity are shown by the number on the dash on the virtual links here. The optimal market clearing outcome are shown by the numbers on the nodes, which are the clearing prices, and also the number at the bottom, which is the optimal welfare value. So so we can see that as virtual link capacities increase, the total welfare increases. And along with that, virtual links allow for clearing loads that are unserved in the base case. So here in this base case where there's no virtual link, we have some amount of unserved load that is successfully cleared once virtual links participate in the market. Also, the price volatility is reduced as we have a large price gap of 20 in the base case, but in the last case, the price gap shrinks to just 3. I wanna note here that the price gap cannot be smaller if we further increase the virtual link capacity, because the bid price of our virtual link is fixed at $3 per megawatt, which dictates the minimum unit price to activate these virtual links. So with the same network, we run another 3 cases where we now fix the virtual link capacity, but gradually decrease the virtual link bid price from 3 to 0. And again, we can see that the total welfare increases because now the cost of using the virtual links are smaller. And in the meantime, the price volatility is reduced. And in the last case, when the bid price is 0, the prices become fully homogeneous. So essentially, the bid price of the virtual link determines the largest decrease of price volatility that specific virtual link can bring about to the system. Then we run the temporal case study here, where we look at one data center co-located with a generator and across 5 time points. At each time, the data center can delay some amount of its computing tasks to the next time point, as shown by these yellow virtual links here. We run 5 cases with increasing virtual link capacity, and we see that the welfare increases and the price volatility decreases. So similar observation as the spatial case. So in the first case, we see great price fluctuation with a large price gap of 70, but in the final case, the price gap reduces to just 6, which is much smaller. Also, again, there is some unserved load in the base case, which is cleared once virtual links become part of the system, become part of the market. So in the end, we test the space-time model on the IEEE 30 bus network across 3 time points, with data centers distributed at the 17 square nodes here in the network. And we run one scenario on the top with no virtual links, and another scenario at the bottom with both spatial and temporal virtual links. So each pair of data centers have spatial virtual link at each time point, and then each data center can shift workloads to the next time point. So the welfare doubles once virtual link participate as shown on the left. And for the case without virtual links, we can see high prices like the node regions, the red nodes in some regions, and the negative prices in the blue nodes. And all of them disappear once virtual links are introduced. So the prices become less volatile. With that, I will conclude my talk, and I'm happy to take any questions.
Great, thank you, Weiqi. There's 4 questions in the Q&A.
Okay, let me. So the first question is, for flexible data centers, how much of the load is computing versus cooling, and what role does local solar PV generation play? Okay, that's a good question. Actually, I didn't look into the specific number of computing loads versus cooling, but if we go to the, I think there's a graph before. So if you look at this graph here, the green part at the bottom is it's indexed as data centers, but essentially this is like the computing part, and I think that also includes some part of the utility. So I'm not sure about the specific breakdown, but I think they are also scaling up at the same time. And what role does the local solar PV generation play? So the local solar PV generation will also be part of where the uncertainty comes from. So and I think yeah, that's we haven't considered much about the local solar PV generation in our model. So we are not sure how that will impact the results of our market clearing. So next question by David. Can you provide the rough number of the percentage of electricity cost that represents the overall business of data center? If the cost is minimal, almost insignificant from the overall volume of business of data business, thus companies are not willing to accept to change their operations, so to save some minimal costs. So that's a good question. Actually, that's also part of the next step that we want to consider, because right now as far as we know, the behavior of data center is that they don't want to. They are reluctant to shift loads either in space or in time. They just want to clear as much loads as possible. But at the same time, we also see some other incentives. So, for example, the data center of Google is trying to do workload shifting, not really to minimize the cost, but actually to minimize the carbon footprint. So they try to shift their loads to minimize the to maximize the use of clean energy, essentially. So that could also be part of our market objective as an incentive for them to shift loads. So the next question is, how did you fix the price for virtual links? That's a good question. So the price of virtual link comes from several parts, and for now we just choose some number. We didn't devote a lot of time in modeling the price for the virtual links, but actually the price can come from a lot of things. So as I said, the data centers are reluctant to shift loads because because of the latency in computing. So as a future direction, we can look for ways to quantify this and then add it to the price. And similar thing for spatial load shifting. So the cost is actually there are a lot of open questions in the cost part. And then so next question.
We have time for about one more question, so pick which one you want.
Okay, I'll just pick in order. Can you give can can you give an intuition about on how controllable the workload of data center actually is? Also, I would imagine that data center operation is subject to uncertainty and the physical data storage location, so the task might not be shiftable. Yes, so as I said, the data center operation in real life has a lot of limits, physical limits like the uncertainty and I mean like the data storage location. So so that will limit what kind of virtual configuration we can place in our market, and also for the yeah, that's
Okay, well,
yeah.
thank you. I think you can answer the rest in the Q&A.
Yeah, I can. Yeah, I'll type the answers on the Q&A.
Perfect.
Thanks.
Thank you. Great job.